Theorem 2.6, and the statement of the theorem goes, if limit of a function f of x is L as x goes to A. Is that what they have? Yes. Okay. And L is greater than 0. All right. So this is the if part, and then it goes on to say then there is an open interval, but and then there is an open interval is that in the book? Yeah, it is in the book. Okay, open interval containing a such that all the values of the function are going to be positive for every x in except possibly at A. Okay. So what is this function saying? The function is saying if the limit of the function is positive, if the limit of let's just write this correctly. So if limit of f is positive, then where the function is defined for the values, so if the limit of the function is positive for the values of x in the interval, the values of the function will also be positive. Okay, so if the limit exists and it is L, and L is a positive number on the y-axis, then there is an open interval. There exists an open interval, right? This one, A minus delta, A plus delta, containing A, so the center point is A, such that all the values of the function defined by the x's in this interval, as in they exist, the values of the function, all of those values of the function will be positive above the x-axis for every x in this interval except for A. So let's start drawing, okay? The first thing I want to do is, before we even draw, if you look So this is condition 1 in our theorem. This is condition 2. These are the assumptions, right? And then if these two conditions are true, then this guy here, open interval, and this open interval, which is also something that is given to us, okay? If these two conditions are true, this will exist, and this is what we have to prove. This is condition 1, condition 2, and this is the result. The consequent that needs to be shown. Okay. Okay, now let's go to this guy here. If I was to take, I want to expand the thing in the box here. So let me write the box here again. I'm going to delete this. Okay, so this is from the consequent condition 1. Condition 1 is limit of the function x is L as x goes to a. So this is our box. And this means let's expand it. So okay, so now I'm on my little bike here. How do we expand that? We say if we do this first, right? If the distance of all the x's from the center point A, if the distance of all the x's from center point A is less than delta and greater than 0, right? So I just expanded that. X approaches A means, formally in the rigorous mathematical way of thinking about values of x approaching the center value A, is that all the values of x are at a delta distance from the center point A, or all the distances of various x's from A are less than delta, and then x never assumes the value of A, which is this part, then we need to bring this guy in. Then all the values that the function will assume as it takes on different values of the x in the domain will be always at a epsilon distance from its center point. It's the limit of the function. Okay, so this becomes that, and you can expand that. And then let's do the graph. So this expanded is this. Now let's go to L. It says L is greater than 0. So here, let's draw the graph here. And it says L is greater than 0. L is positive. So, Mr. Jake, can I put L right here?
No, because L is positive, right?
And the answer is, 1 second. Yes, Jake.
No, because L has to be positive, right?
Because, very good. Because the numbers here are below the x-axis. So this won't work. And our only choice for putting L has to be up here. Okay. And then it says then there is an open interval, this guy containing A. Also, we can draw out the function, right? So let's just say this is our function. And it says the values of this function f, this is the graph of the function, the values of the x values containing in the domain within this. So in other words, we need so this is A minus delta and A plus delta. So all and then there's an open interval which I just made containing A. I just put A in there such that f of x is greater than 0 for all x in this same interval. So if you look at the way the graph is right now, is f of x so this is a question for you, Jake. Is the f of x defined by all the x's here, all the values of f of x that we get when we plug in x's from this interval, excluding this point and maybe this one, A, are they all positive values of f of x?
Yes.
Yes. So again, this is one of those rhetorical questions that has the answer yes. And so that is what we have to prove. We have to if the limit exists and the limit is positive, then all the functional values that will fall up here, and these are all f of x are all positive here because they're above the x-axis. You have negative f of x's down here, right? Okay, all right. So let's do the proof quickly, and then it's 11:13. Let's see. Okay, Liliana is still there. Okay, Liliana, as soon as you're done with the proof, you can take off, all right? Oh,
Okay, that works.
yeah, and then I'll see you in class next semester, okay? And thank you for that sample because that really helped me a lot, the one that you wrote. Okay, let's continue. And let's see, where is it? Okay, the proof. So, so I'm going to delete all this because we need space. Okay. So what I'm going to do is I'm going to rewrite the theorem, giving all the formal stuff. So in the theorem, it said the limit of f of x equals L as x goes to A. So that's number 1, comma, L is greater than 0. That's number 2. And then this implies that in the open interval, delta, what is it? Sorry, A minus delta and A plus delta, the x's, so the x's in this defined values of f that are positive. Okay, all right, so the proof goes, so this is our shorthand. Maybe I should write this in red. Okay, proof. Very short proof. Hopefully it will end soon. Let's see. So now we're going to say if L is greater than 0 and we let epsilon equal to half the value of L. Okay, so what has happened here? So when we start the proof, what do we usually do? We elaborate the conditions, right? Is that right, Jake?
Yeah, that's what I said.
Okay. And then even this is kind of a condition. And then this is what we have to show. So we're setting up, we want to get to f of x is greater than 0. And we're going to use everything they've given us, which is all these guys here. So epsilon is coming from which box? Box condition 1, 2, or 3, Mr. Jake?
Epsilon is coming from.
So there is no epsilon here. We have deltas here. Yeah. We have just L is greater than 0. L is a positive number. So our only choice is
condition 1.
Condition 1. Very good. This is an SAT question. Multiple choice. Okay, so and if you expand this guy, let me expand it here on the side. It means if then now again, Mr. Jake, where is the epsilon coming from?
Yeah.
Right there, right? Very good. Okay, so if delta is the limit is 0 and epsilon is half of L. So if we were making a picture, let's make the picture here. If I put L, so can L be 0? That's a good question. Mr.
No,
Jake. No, because 0 is not a positive number. Can L be 1?
Yeah.
Can L be, so L can be 1. It can be any number between 0 all the way to infinity here, right?
Yeah.
So if we, so all we want is L to be positive. And we want a reasonable positive number. So for instance, if I chose